Hey guys, Douglas here. We're going to be talking about section 5.6, which is rational expressions and rational functions. So the thing about a rational function is, as you can see from this first example, these are functions that are already in a form where you have on top a polynomial. So you notice it has x squared, and a number, so it's a standard polynomial, and it's a fraction. So on bottom it'll also have a polynomial. The things we're going to talk about today do not apply unless this is the case. So if you have a polynomial on top and a polynomial on bottom, these are called rational functions, and we're going to talk about how to do things like find the domain, find asymptotes, and graph them. Now this last one is going to consume the majority of our time, because if you can graph these, it's because you can do the other three things. And so most of the work we're going to do today is going to involve around the graphing part. And as we're doing the graphing part, we'll talk about how do we find vertical, how do we find horizontal, how do we determine the domain, and other things to help us find out the graph of the function. It's going to be a big day, so let's get started. First thing to point out here, we need to know some notation we're going to have today for our notes. This is referred to as arrow notation. If you haven't seen it, it's because you haven't been paying attention in class. I use this quite often. Arrow notation is a way to markate how a function is written and to illustrate a lot of information very quickly. So we have a few of these. So we have as x approaches a minus, x arrow a plus, x arrow infinity, x arrow negative infinity. And I'll be honest with you, I prefer to write positive infinity and negative infinity as plus and minus infinity. F of x arrow infinity, f of x arrow negative infinity, and f of x arrow a. Let's go through these one at a time. X arrow a minus. So what this tells me is this is what's happening as x approaches a from the left-hand side. So in terms of a graph, this is really important, but in terms of a number, it's equally important too. So let me show you guys a very brief graph, one that will illustrate all these properties, and is one that's really important for today as well. This is the graph of something called the reciprocal function. Now, the reciprocal function is written as 1 over x. It is considered to be the standard rational. Now, this function looks as follows. Over here, and up here. So, a good way to look at this picture is to ask questions like these ones. So, for example, what's happening as x approaches 0 from the left? What's happening as x approaches 0 from the right? Well, what this says is, as we get towards 0 on the x values from the left. So, remember, here's 0, right? So what's happening left of 0, but getting closer to 0? So here's left of 0. All these values over here are left of 0. And so negative 4 is left of 0. Negative 3 is left of 0. Negative 2 is left of 0. Negative 1 is left of 0. But what's happening here is what happens as we get close to 0. So what it's asking is what's happening as we get towards like a half, like negative 1/2, or negative 1/4, or negative 0.1. Like what's happening as we get real close, but still staying to the left-hand side? The reason that's important is it's different in this graph between the two sides. On some graphs, they're the same, but not on every graph. And so as we approach 0 from the left, we're going towards negative infinity. You can see that this graph, as we approach left, right here at negative 1, it's at negative 1. At negative 1/2, it's like at negative 4, or negative 2, somewhere in here. And if we got even closer to 0, we're going to get closer and closer to this negative number that's really, really small. And so as we approach from the left, we're approaching one number. But as we approach from the right, we approach a different number. And that's what this symbol means. As x approaches a from the right, so what does this mean? If you look at this graph, you can clearly see that all of these numbers are right of a. But as we get close to 0, something happens to our graph. Our graph goes up over time. As we get from positive 2 to positive 1 to positive a half to positive a quarter, as we get closer and closer and closer, each and every time we get closer to 0, as we get closer to 0, what's happening to the graph? It's describing a trend. And that's a good way to think about this. It describes the trend. Trend doesn't mean you're going to get an exact answer. It means you're going to get a relative answer, right? This tells me we're going to negative infinity. It tells me that as we go towards 0 to the left, like as we get closer and closer to 0 on the x-axis, our graph goes farther and farther down. As we get closer and closer to 0 on the right, our graph goes farther and farther up. That's why it's positive infinity. Now, what does x going to infinity mean? It means as x increases, or as x goes to the right. The first one is how you think about the numbers. The second one is how you think about the graph. So in this exact same picture, we can ask two more questions. What happens as x goes towards infinity? Well, that's what happens when the x values increase. So what's happening as we go from 1 to 2 to 3 to 4, farther and farther and farther to the right? You might notice this graph is gradually going down over time. But you might also notice it is gradually leveling off over time. Meaning that as we go farther and farther to the right, what's happening to our graph? We're getting closer and closer to 0. This other one, as x goes to negative infinity, is when x is decreasing. Or if you think about the graph, as x goes to the left. So in this particular example, you can see that as x goes towards negative infinity, something similar happens. As we get farther and farther and farther and farther to the left, what's happening to our graph? Well, it's getting closer and closer and closer and closer to 0. And so as x goes towards negative infinity, our value is 0. So that's how you read a statement like this. As x goes towards negative infinity, so that's to the left, our value is equivalent to 0. This is referred to as arrow notation. So f of x going to negative infinity and f of x going towards positive infinity is a slightly different thing. So this is as y increases, or as y goes up. This one is y decreases, or as y goes down. Because negative 12 is a negative number, but it's still decreasing because it's going down from negative to negative to negative. A large negative number is decreasing. F of 0 means, or sorry, f of x goes towards 0 means as y equals a, or as y approaches a. So we can have it looking specifically at from the left, we can have it specifically looking at from the right, we can have it what's happening as we actually get there. And so these are some of the things that can really differentiate different questions. Because in this picture, if I ask what's happening at 0, there's two different answers, for the x-axis anyways. Because as I approach 0, well, if I'm coming from the left, I'm going to negative infinity. As I'm coming from the right, I'm going towards positive infinity. I get two different answers, so I have to have two different ways of talking about it. One that talks about, okay, what's specifically happening from the left. And another one that's talking about, okay, what's specifically happening from the right. Now, if I wish to have x approach 3 from the left, what you can ask is what's happening at 2, 2.5, 2.9, 2.99. All of these are to the left of 3, but they do get closer to 3 each time. So we could, if we want to know without the graph what's happening as we approach 3 from the left, we just test values to the left of 3, but make sure we keep getting closer to 3. If we wanted to approach 3 from the right, we can plug in values like 4, 3.5, 3.1, and 3.01. These are all definitely to the right of 3, but they keep getting closer and closer to 3. And you could continue this pattern farther if you wanted to. Just make sure you keep getting closer and closer to the number you want to approach. And so we now have a way to talk about the graph using these arrow notations and the numbers using these arrow notations. Because if x is approaching 3 from the left, I can just test a couple of values to the left of 3. If x is approaching 3 from the right, I can test a couple of values from the right. And you can see an example of that right here. This is talking about if we're approaching 0, what's happening. So notice how each of these values, so this is to the left of 0. Well, if you look at the number line, with 0 in the middle, to the left of 0 is going to be negative numbers. But to the right of 0 is going to be positive numbers. So if I want to x approach 0 from the left, I want to look at numbers like, negative 1, negative 1/2, negative 1/10. Numbers that are near 0 but getting closer to 0. If I want to approach 0 from the right-hand side, I want to do the opposite. So 1, 1/2, 1/10. Getting closer and closer to 0, but staying to the left of 0. Getting closer and closer to 0, but staying to the right of 0. This has a definition. It is called local behavior. Local behavior is defined as what's happening towards the middle of the graph. Think about this example. If we consider the end behavior, remember, end behavior is the outside stuff, what's happening as we go far to the right and far to the left. Well, in this example, the end behavior is boring, right? To the left, we've leveled off. To the right, we've leveled off. There's nothing really to talk about. There's nothing interesting happening to the picture. Whereas in the middle, this is interesting. It's doing something crazy in the middle. So in this middle piece here, this is referred to as local behavior. Whereas as we go towards infinity, this is called end behavior. And it's really light because I want it to be light. Now, you can define your own local, because maybe the interesting stuff is happening right here. So we can make this our little local. Or maybe it's happening over here. You can make that our little local. We can define local to be wherever it is interesting. But the key thing is, end behavior is always predictable. We talked about that before with polynomials. Same with rational functions. It's the middle stuff that can get weird. And so that's where we're going to spend a lot of our time. Okay, we've had some definitions. Let's keep it going. So there's one graph we've had. This is one of the graphs we're going to talk about a lot today. But there is a second one. This is called the reciprocal squared function. This is 1 over x squared. So before we go on, let's finish up with this one. So as we're going towards 0 from the left, we are going towards negative infinity. So as we approach 0 from the left-hand side of 0, we are going down over time. As we're approaching 0 from the right, so from the right, going towards 0, we go towards infinity. As x goes towards infinity, we level off, we go towards 0. As x goes towards negative infinity, we level off, we go towards 0. But let's talk about the other two we have over here. Okay. So these two would be considered end behavior. These two would be considered local behavior. All right, let's compare this to the 1 over x squared function. The 1 over x squared function looks like this. It has to the right of 0, you notice it looks exactly the same, or very similar at least. To the left of 0, it looks different. So this is the reciprocal squared function. Now let's talk about those components again. What's happening as x approaches 0 from the left? Well, as we get closer and closer to the 0 value, our value approaches infinity. What about from the right? Well, as we approach it from the right, it also approaches infinity. What about our f of x? What about our x? What happens as x approaches infinity? Well, as x approaches infinity, well, this function approaches 0. What about x approaching negative infinity? Well, also approaches 0. And so you notice that the reciprocal function has this inverted relationship. One side goes towards negative infinity, one side goes towards positive infinity. Whereas the reciprocal squared has a different function. They both go to the same value. This is one of the properties that we'll spend some time on today, but I will come back to it. And so let's keep these two functions in mind as we go farther. Okay. Next bit of notes. We have now the definition of vertical asymptote. Okay, notice the definition of vertical asymptote is written in arrow notation, so if you don't understand arrow notation, you can't understand this definition. Let's go ahead and take a look. The vertical asymptote is a graph of a line x equals a, where the graph tends towards positive infinity or negative infinity as the input approaches a. In other words, as x approaches a from the right or left, f of x approaches positive infinity, or as x approaches a, f of x approaches negative infinity. So, as we get closer and closer to a, the graph goes up, or as x approaches a, the graph goes down. But notice this is to infinity. So it's not just going a little down, it's going all the way down. It's going straight down. This example here in the text right here is really helpful here. In this example, this is actually our 1 over x function. Here notice that as we go up and down, as we approach 0, it is going towards infinity. And so in this example, 1 over x has an asymptote at x equals 0. Why is that? Because to the left of 0, we are tending downwards. Notice straight down almost. This means you're going towards negative infinity. As x approaches 0 from the left, f of x approaches negative infinity. And then on the other side of that, as x approaches 0 from the right, f of x approaches positive infinity. So this is by definition an asymptote. But it is not the only asymptote. Like, depending on the function, you can have different asymptotes in different places. Take a look here. This red line is considered an asymptote, meaning in this picture, x equals 2 would be an asymptote, a vertical asymptote. Because in this picture, you can clearly see that this one is going down as we get close to 2. This side is going up as we approach 2. In this picture, negative 2 is our vertical asymptote. Because in red here, as our values approach negative 2, look at this graph. It starts off around positive 3. Then as we get close to negative 2, it shoots downwards, going towards the bottom of the screen. And this one over here, same thing, but in the opposite direction. And so these are all considered to be vertical asymptotes. These are ones that go straight up and down. These are breaks in the graph. You have to lift your pencil to draw these. Like if I want to draw this kind of function, I have to lift my pencil up so that I can get to the other side. Like this is an asymptote. This is my vertical asymptote. By definition, there's a second type of asymptote. These ones are referred to as horizontal asymptotes. They're right here. Graph of the line y equals b, where as x approaches infinity, f of x approaches b, or as x approaches negative infinity, f of x approaches b. So these are places where the graph goes as we go farther left or right. This is what we're approaching, this is what we're getting closer to. This is a number value. And so putting both in the same picture, there's some of these in your textbook, but I'll put one on here just for me. Okay, let me get my nice graph up here in red. Okay, so in this picture in red, we would have the function f of x. Okay, notice that going straight up and down through the middle of this function, we have this little blue line here. This blue line is a vertical asymptote. How do I know it's vertical asymptote? Notice that left of the blue line approaches the blue line. We get closer and closer to that line over time. Right of it does the same thing. It gets closer and closer to the line as we keep getting closer and closer to it. It's like as if the two want to merge, like traffic. Okay? Now, where is this? What is it called? Well, in this case, you notice that it has an x value of 2. And so the line here is x equals 2. Notice up here, we have a similar one. Going left to right, this purple line is the horizontal asymptote. Because again, notice that in this time, going left or right, it's approaching, it's getting closer to until they eventually line up together. And so we can see it's getting much, much closer over time. And in this case, it has a y value. Notice it never crosses the x-axis. And this y value would be y equals 2. And so in a picture, you can always quickly identify the horizontal and vertical asymptotes by looking for these breaks. Where are they lining up? And so in this picture, you can see how the red line is a vertical asymptote, and that vertical asymptote would be at when x equals 2, as it listed right here. Boom. Whereas if you look at the green line would represent a y value. And so you notice it happens at 4. This is a horizontal because it's going left to right. And it's at 4. Right there. So the question asks you to find the asymptotes, and they give you a graph that's as simple as it is. The asymptote going up and down is the horizontal, and it's the x value, so it'll be x equals 2. 2. Whereas the y value would be the one going left to right, and it's 4. Remember, it's a break in the graph. It's a place where this function fundamentally shifts and makes a big change. Now, there's one more big thing that can happen. It's referred to as discontinuity. Where is it? Is that written down? I'll find it later. Okay. Next one that I want to talk about, I'm going a little out of order of the book apparently, is referred to as removable discontinuity. These are holes in the graph. These are places where the graph simply doesn't exist. And so if you're looking at a graph of a function, this does happen on some functions, depending on the functional value and how it kind of fits together. So real quick, I want to showcase kind of an example of one graph that showcases all three of these things. And to do that, I'm going to pull up a graphing calculation that I have. And there it is. Okay. In this case, I already have 2 lines on here. I'm going to get rid of those. This is my TI calculator. So this is like what I use with WAVIDIMO. So in this case, I want to look at the graph of x squared minus 1 divided by x squared minus 2x minus 3. Okay, so up here in red should be our nice little graph. Let's point out a couple things. With a graph like this, it's a little harder to tell sometimes, but you can clearly see there is a vertical asymptote right here, splitting these two apart, which appears to take place at this value, which is at what appears to be 3. So in this picture, x equals 3 would be considered to be a vertical asymptote, because the place where our line clearly fits right in between. And in fact, I can type that in. I can type in x equals, sorry, I should have. This calculator won't do it. Never mind. Sorry. I may have to switch to Desmos for it. But that's clearly a graph. And I can see left and right. I can get the exact same thing. And so this gives me a function which has both. But there's one more thing it has. If you look over here at the table, you notice that at 3, there's an error message. Let's go ahead and pull up Desmos real quick. Okay, I've got the same graph pulled up in Desmos now. And now let's look at this x equals 3. You notice that it splits my graph right down the middle. And this is clearly an asymptote because it approaches as the x value gets closer and closer and closer to 2, or sorry, to 3. My graph goes farther and farther and farther negative. Notice that even down here, my value is 2.829. So it's getting close to 3, but my y value is negative 10. Like, that's much farther down than it should be. And like, if I keep going even farther down, even down here, when my x value is at 2.965, my y value is at negative 56. So as I'm getting closer and closer to this value of 3, my y value is getting farther and farther negative. There's also one on here going left to right. at y equals 1. So you can see by the same logic, as we go farther and farther to the left, my x values get more and more negative, but notice what's happening to my y. My x value is at negative 9.49, but my y value is at 0.84. And as I go even farther to the left, my x values keep going up, negative 24 now, but notice what's happening to my y. It's just getting closer and closer to 1. Closer and closer to 1. And no matter how far over I go, there'll always be this slight gap in between them. But I notice that every time I go farther to the left, I get closer, just a little bit closer to 1. And the same thing happens as I go to the right. So in this case, my green line indicates I have a horizontal asymptote. I am approaching this value left to right. My blue line indicates I have a vertical asymptote. I am approaching this value up and down. Notice that it deals with two different situations. My blue line, my vertical, is describing as I approach an x value, what's happening to the y. My green line is as I approach a y value, what's happening to the x. And the last thing I should point out here is what's happening over here at positive 1. There it is. Take a look here at negative 1. Let's see if we can pop it just right. Come on. There it is. Notice it looks like there's a graph there, but at this one dot, there appears to be a place where we have this thing undefined. This is referred to as removable discontinuity. It's a hole in the graph. And it actually is there because of the function that we started with, this function right here. This function actually predicts that at this value of negative 1, I won't be able to get an answer. And I will teach you guys today about how to get that answer and show it every time. It's not as hard as you think. It just requires some practice. But this is referred to as discontinuity. So asymptotes can be discontinuity because it's a place where you have to lift your pencil to draw them. But there can also be ones that appear just as random holes, where the graph just stops working. So this is removable discontinuity, and these two are asymptotes. Okay. All right. So how do we find those things using a function? This is where the fun begins. It's where the meat of the homework tonight begins, and where your notes kind of take a pause, because most of the stuff we've talked about is the big part of notes. Now we're just going to talk about how to use it. So let's go back to our notes. So how do we find a vertical asymptote? How do we find horizontal asymptotes? How do we find discontinuity? Each one of those is going to involve specific skills, and most of them are going to involve something everybody loves, factoring. So let's take a piece out. Fresh notes. All right. So let's go through them one at a time. First of all, one of the big things you're asked to find today is domain. So how do you determine the domain for a rational function? Well, first of all, the domain is typically from negative infinity to positive infinity, except when the denominator equals 0. That's a big detail that we're going to talk about how to do that here in a little bit. But if the question asks about the domain, it's typically from negative infinity to positive infinity, with one exception. If the question asks to find things like, how do we find a vertical asymptote? Vertical asymptotes occur in the same location, when the denominator equals 0 and the numerator does not equal 0. How do you find things like holes? Holes occur when they both equal 0. How do you find things like a horizontal asymptote? Well, this has to do with the degree. So for the horizontal, there are 3 scenarios. And just in a little bit, I will showcase kind of where these all appear in your book. And so let's go ahead and start with these 3. The first scenario, the top degree is less than the bottom degree. In that case, you will have a horizontal asymptote when y equals 0. So this is also called the x-axis. If the top degree is equal to the bottom degree, then it's going to be referred to as P over Q, which I'll talk about later. So it's some kind of fraction. And the last one is if the top is bigger. This has no horizontal, but it does have slant. Okay, let's point these out in the text. Vertical asymptote. This is on page 420. The holes for the removable discontinuity. These are on page 421. The horizontal asymptote. These are on page 423. They're in the middle of your text. If you just look for those captions of vertical asymptote, horizontal asymptote, removable discontinuity, they're all in there. Okay. Let's keep it going. Because these are all things we're going to be doing today, and I want to get all the notes done before I start looking at a problem, because we're going to do each one for each problem. Okay, intercepts. This is the last big set. Two types, x-intercepts and y-intercepts. X-intercepts. These occur when the numerator equals 0 and denominator does not equal 0. Y-intercepts occur when x equals 0. This is everything we need to solve our problems today. But it's a short list, but it is not an easy list. These is included on page 425. At this point, I'm now immediately going to jump into some problems. Because quite frankly, these problems, because they have so many parts to them and so many different things to find, it's best to get a lot of practice in. So let's take a look at 3. Number 12, number 16, and number 18 from your homework assignment. And on each of these problems, and the instructions say to do one thing, I'm just going to show all of this. I'm going to show how to find the domain, the vertical asymptotes, the holes, the horizontal asymptotes, the intercepts. I'm going to do it all for each one of these, even though the homework may not say to do it. So on like ones before 12, they only ask about the domain. So just do the domain steps. Okay? So let's go to number 12. This section is beefy. It's got a lot of parts to it. And so because of that, they go through a lot of really good examples in the text. Please just be sure to use that to help you out. They really do showcase a lot, and it's great to have. So let's look at number 12. Number 12 says, find the domain, vertical asymptotes, and horizontal asymptotes of the function. I'm going to go even farther because I'm also going to find the intercepts as well. and if there's any holes, of course. Okay, number 12. This one's a really basic one. It says we have the function f of x is equal to x over x squared minus 9. So let's do it in pieces. So let's first start with the domain. How do we determine the domain? Well, the domain is everywhere, is all the numbers except when the denominator equals 0. So what do? Check when the bottom, and only the bottom, equals 0. Whatever the whole bottom thing is, check it. See when it equals 0 and find those places. So in this function, my domain, all I care about, it's x over x squared minus 9, but all I really care about is the x squared minus 9 part. It's the only part of the thing that's going to affect the domain. So the domain is when the denominator equals 0, so I take the denominator, which is x squared minus 9, and I equal it to 0. And so what do? I now need to solve. So I'm going to add 9 to both sides. I get x squared equals 9. I then square root both sides. I get x equals the square root of 9. Remember, when you take a square root, you get two answers, a positive and a negative, which means mine are plus or minus 3. So the question is, what's the domain? Well, it's everywhere except plus or minus 3. How do we write that? From 2 chapters ago, negative infinity to negative 3, negative 3 to 3, from 3 to infinity. This tells me that in my graph, I can clearly see that I will have two places where the domain fails. Remember, the domain fails if I have to pick up my pencil when I'm drawing this thing. So this is places where the domain is going to fail. This is the domain of this function. Notice how I found it. I took the denominator, I set it equal to 0, solved, found my two answers. There won't always be two answers, sometimes there'll only be one. And once I've got that answer, I then just write it out. This top answer is acceptable. I think your book even leaves it this way, but the bottom answer is better. So, domain's done. Notice how we did it. We set the denominator equal to 0, and then solved. Next, let's do vertical asymptotes. The nice thing is, if you've already done a domain, then you've already got your vertical asymptotes. The vertical asymptotes are, again, when x equals 0. Should I say, when the denominator equals 0. So what did I get? Well, I got x equals plus or minus 3. So where are my vertical asymptotes? My vertical asymptotes occur when x equals 3 and when x equals negative 3. So notice how the domain and the asymptotes fit together. The domain skips over these places, but the asymptotes include those places. So this is why, doing the domain helps you find the asymptotes. 3. Okay, horizontal. Well, I told you when we did the horizontal, there are 3 things to check. These 3 things are based upon the degree of the top and the degree of the bottom. So is the degree of the top bigger, smaller, or equal? Well, let's look at this. We have x over x squared minus 9. In this case, the degree of the top is 1 because the power is a 1. Oops, out of sight. So, in this example, so we have x over x squared minus 9. We have x, it has a degree of 1, over the bottom has a degree of 2. Remember, the power tells you the degree. So notice that in this example, the top is less than the bottom. I go to my list. If the top is less than the bottom, my horizontal asymptote is at y equals 0. Simple as that. So, if the top degree is less than the bottom degree, then that's y equals 0. So, according to number 12, I would be finished, but I'm going to go farther. I'm going to showcase how to find the intercepts. So, how do we find the intercepts? So this is unnecessary. This is extra work for this problem, but you notice as we look farther down ones ask you to find the intercepts. So there you go. So number 4, intercepts. Let's break it into 2 parts. X-intercept. Well, the x-intercept is when the top is equal to 0. So if we have x over x squared minus 9, all we look at is when the top equals 0. And it turns out, that's it. There's nothing to solve. There's nothing to add or subtract or multiply or divide. X is already by itself, so that's it. So for the x-intercept, it's when the top is equal to 0. Whereas for the asymptotes, it was when the bottom is equal to 0. So for the y-intercept, all we do is everywhere there used to be an x, I replace with a 0. So we have 0 over 0 squared is 0 minus 9. 0 minus 9 is negative 9. 0 divided by negative 9 is 0. So this is when y equals 0. And so we have an x-intercept of x equals 0. We have a y-intercept of y equals 0. And we can go to those places on the graph and find our intercepts. Again, to find the x-intercept, if we take the top and set equals 0. To find the y-intercept, we take the bottom. Sorry, we take every x and make them equal 0. Okay. 16. I said the goal today was to get a lot of practice with these, so let's go back. We're going to look at 16. We're going to do domain, intercepts, asymptotes, and if it has any holes, we'll list those too. 16. Start with domain. To answer the question about domain, all we do is we take our original function, which was 3x minus 4 over x cubed minus 16x. To answer questions about the domain, all we do is we take the denominator, which is x cubed minus 16x, and we set it equal to 0. And then we start solving. So in this case, I could factor an x out. I could then use our fundamental theorem of arithmetic to split this into x equals 0 and x squared minus 16 equals 0. Now, I know this first one is a place where I'm going to have problems. I can take the second one and solve it. I add 16 to both sides, take a square root. So this tells me there's going to be 3 problems in the domain. And because there's going to be 3 problems in the domain, I now know those are also going to be places where I'm going to have vertical asymptotes. Vertical asymptotes, remember, are places where the denominator equals 0. Well, that means that I'm going to have vertical asymptotes at x equals 0, x equals 4, and x equals negative 4. So the domain of this function would be from negative infinity to positive infinity, but there's places where I can't cross. I can't cross negative 4. I can't cross 0. I can't cross 4. So I can't cross negative 4. I can't cross 0. I can't cross 4. So there's my domain. Notice that each number that appears in my domain as a problem came from my equation. Notice that each number that appears in my asymptotes came from my equation. And so domain and vertical asymptotes can be found in the same step. Now, what about horizontal asymptotes? To find the horizontal asymptotes, I need to look at the function and ask what's the degree. On top, my degree would be 1. On bottom, my degree would be 3, which means that for this function, my asymptote would be at y equals 0. Again, using my list. If the degree on top is less than the degree on bottom, then it's y equals 0. So y equals 0. And so if this was all the question asked, I'd be finished, but I'm going to go ahead and take it a step farther, and I'm going to find my intercepts too. So, what are my intercepts? Well, for this problem, to find the intercepts, let's start with the x-intercepts. The x-intercepts occur whenever the... Oh my god, brain stopped. Whenever the numerator equals 0. So, when the numerator equals 0, that means that we have when 3x minus 4 equals 0. Remember, the bottom piece of this function is used to find the vertical asymptotes and to find the domain. The top piece of this function is used to find the x-intercepts. So then we solve. When we solve this thing, we get x equals 4 over 3, which means that this will be a place where I cross the x-axis. My y-intercept can be found by just taking 0 and plugging it into the equation. So we get 3 times 0 minus 4 over 0 cubed minus 16 times 0. Okay, so in this case, we have on top, we get negative 4. On bottom, we would get 0. You are not allowed to divide by 0, which is why this is undefined. Okay. I'm going to now look at 16. I'm going to look at the picture of 16. I'm going to graph it. And we'll see that this domain is right. At negative 4, there is an asymptote, which causes there to be a graph with a break in the domain. At 0, there is an asymptote, which causes there to be a break in the domain. At 4, there is an asymptote, which causes there to be a break in the domain. It will have a horizontal asymptote when y value is 0, so that tells you that at the x-axis. And in this case, it'll have intercepts at x is 4/3, but that's it. It'll cross the axis nowhere else. And the y-axis won't be crossed at all. So let's graph this thing. So let's put it in. We have on top 3x minus 4. On bottom we have x to the third minus 16x. Let's look at our asymptotes. Our asymptotes are at x equals 0. That's one in black. When x equals negative 4. One in red. When x equals positive 4. One in blue. And so you can see how, yes, there's an asymptote here, there's an asymptote here, there's an asymptote there. You can see here, where if I do y equals 0, you notice that it does cross it. But remember, asymptote doesn't say it can't cross. It just says it needs to approach. Notice that as we go farther and farther to the right, we do approach the green line. Our purple original function does get closer and closer and closer to that green line. But notice it never actually gets there. It never actually gets to 0. Even here is at 9.56. And my y value is 0.034. It's near 0, but it's not 0. And if you go farther to the right, it keeps getting closer to 0, but it never quite gets there. Over here, same thing. So it's definitely an asymptote. We are, in fact, approaching 0. But we never really get there, left and right. Remember, these kind of things don't tell you what happens in the middle. And so this horizontal asymptote can be crossed in the middle, but at the ends there's going to be a place where it goes close to. And so you can see red line, black line, and blue line are all vertical asymptotes. Green line is a horizontal asymptote. And notice the single intercept we have is at 1.3 repeating, which is 4/3, of course. We were able to predict all of this stuff using the formulas that we have, which is still pretty neat. And you'll notice that if you look at that picture one last time, my graph never crosses the y-axis. I never actually cross it. I get real close to it, but I never cross it. And farther down, same thing happens. So number 18, same thing. Notice that these can take up a significant amount of paper, especially if you're showing a lot of your work. You are welcome to grab a hold of your stuff and graph it whenever you're finished to check your results. It is strongly encouraged, but do make sure you're using it to check, not just to copy your work down. Okay, number 18. Doing it again, one piece at a time. And notice that for most of your homework problems, they don't ask you to do all these things. They ask you to do a few of these things. And so make sure you can take those pieces and find those few basic things. Okay. 18. We have f of x is equal to x minus 4 over x minus 6. Beautiful. Okay, so we're going to find all these things. So domain. All right, for my domain, to find the domain, I just take the denominator and set equal to 0, and that is equal to 6. This is a place where my domain fails, so this means this is my vertical asymptote. How do I write my domain now that I can't include 6? Well, I have to start at negative infinity. I can go up until 6, but I cannot include 6. So I've got my domain and my vertical asymptote from one part of the problem. Okay, next, horizontal asymptote. Now, this is a case where the top degree and the bottom degree are the same. So you notice that on top, my top degree is 1. My bottom degree is also 1. Because the top, the biggest power is a power of 1 on the x and a power of 1 on the other x. So they have the same ones. So where's the asymptote? Well, it says that y equals, and notice the peculiar phrase, it says p over q. P over q, p is the coefficient of my degree. Q is my coefficient of my degree. It's the number in front. So, on this one, my horizontal asymptote would take place at my coefficient. I have a single x, which means there's a 1 on top. I have a single x on bottom, which means I have a 1 on bottom. So my horizontal asymptote would be at y equals 1. That comes from the coefficient of the x divided by the coefficient of the other x. To re-illustrate this point, because it doesn't happen very often, look here at 19. 19 is one of your problems, but I will give you your answer if you're paying attention. The horizontal asymptote on 19, right, the horizontal asymptote would take place at negative 2 over 3. How do I know that? What's the coefficients? Well, on the x, we have a negative 2 as a coefficient, which is where my negative 2 comes from. And on the x on bottom, we have a 3, which is where my 3 comes from, which is why it's negative 2 over 3. This one is a 1 because it's 1 over 1, which reduces to 1. If I go farther down, like let's say 24, same thing. If I wanted to find the horizontal asymptote, it'd be negative 2 over 3 as well. But if I look at one like 27, it'd be negative 2 over 1, because negative 2 is in front of the x, and 1 is over the x, so negative 2 over 1, there's the horizontal asymptote. For 29, it would be 2 over 6, because x squared, we use the first coefficient, 2 over 6. There it is. Last thing, to finish this problem. So this is all the question really asks for, but I'm going to continue. Intercepts. So there's two of them. There's the x-intercept and the y-intercept. To the x-intercept, I take the top, which is x minus 4, and I set it equal to 0. What do I get? X equals 4. So this is the point 4, 0, which is my x-intercept. My y-intercept, everywhere there used to be an x, I replace with 0, so 0 minus 4 over 0 minus 6. 0 minus 4 is negative 4. 0 minus 6 is negative 6. This becomes 2/3, or 0, 2/3. So I've got my domain, my vertical asymptote, my horizontal asymptote, and my intercepts all listed out using my function. One more time, from the top. Desmos, here we go. I get rid of all these. Original equation was x minus 4 divided by x minus 6. And if I look at this graph, where's my asymptote? At x equals 6. So you can see that black line. That's clearly an asymptote. Where's this asymptote? At y equals 1. Clearly an asymptote. Where are my intercepts? Well, my x-intercept should be at 4, which it is right there. My y-intercept should be at 2/3. So I was able to find all the components that I needed for this problem inside of this very simple example. So I found 4, 2/3. I found my 6 for my x equals 6. And I found my 1 for my y equals 1. I was able to find the domain, vertical asymptote, horizontal asymptote, and the intercepts using a process. No matter how complex the function gets, this is always the case. Okay. Now, you'll notice that on 30, 31, 32, and 33, and 34, these set, it talks about the slant asymptote. Let's add to our notes. How do you find slant asymptotes? Slant asymptotes are found using long division. Slant asymptotes are found using long division. Let's look at number 30. What you'll do is you will do long division. Your quotient, which remember is your result, will be your slant asymptote. I'll showcase what a slant asymptote looks like over here in this corner. A slant asymptote is when your graph appears to approach a value, but it's not going up or down. So in this case, we'd have a slant asymptote because there's clearly a boundary line that rests in between these two. Like there's clearly something going on here, but it's not going left or right, and it's not going up and down. So it's not horizontal, it's not vertical. This purple line is referred to as a slant, or a slant asymptote. So how do we find that? Well, just do long division. So let's look now at number 30. On number 30, we have the following equation. We have 24 x squared plus 6x divided by 2x plus 1. Okay, All we have to do to find the slant asymptote is do long division. Well, let's do long division. So we take 24x squared plus 6x. We're going to divide this by 2x plus 1. Okay, let's do it. On this function, I do the following steps. So I want to make this 2x match this 24x squared. So I'm going to choose to do 12x. If I take 12x times 2x, I would get 24x squared, exactly as I want. If I did that, though, I would have 12x times 1, which is plus 12x. Anytime you do long division, you subtract your result. So I'm going to subtract this answer. 24x squared minus 24x squared should be 0, which is good. 6x minus 12x should be negative 6x. And then there's nothing over here, so there's a 0. I'll drop that down. 2x and 6x, the last piece I have. How do I get those to match? Well, that would be negative 3. So negative 3 times 2x should be negative 6x. Negative 3 times positive 1 would be negative 3. We then take the result, multiply it by negative 1, and then put them together. Negative 6 minus negative 6 would be positive 6, would be 0. And double negative would make it positive 3. So remember, it's your quotient that is your answer. So this is your slant. Let's show where that comes from. Let's see what this looks like in the graph too. So once again, I pull up Desmos. My function was on top 24x squared plus 6x divided by 2x plus 1. So if I zoom out a little bit, you can clearly see how there's a slant to this thing. Like, it's not a clearly up and down asymptote or a left or right asymptote. There's clearly a slant going on here. And where is that slant? Well, it's at 12x minus 3. Look at that. I'm going to zoom in a little bit so you can see a little better. Look at this. See my blue line? How it gets closer and closer to that green line? And the farther up we go, it gets closer and closer still, until eventually you can't even tell the difference between them. That's an asymptote, right? We're approaching the line. Same thing happens down here. And so this is our slant asymptote, which we can find using long division. And so if the question asks about any slant asymptotes, just do long division, and you'll always find your answer in the quotient. The remainder in this case is not useful. The plus 3, nothing. Who cares? It's the 12x minus 3 that is the quotient. It's the 12x minus 3 that is your slant asymptote. Okay. All right, graphing. These are the fun boys. These are the ones that are going to guarantee you want to hate something. Probably me. So, how do we graph these? Well, it turns out how you graph them is by doing everything we just did, and then just putting it onto the paper with one extra little step at the very end. So, we're going to approach number 40 the same way we approached number 12, 16, and 18. Just at the end, we're going to put it onto a graph, and I'm going to showcase kind of how that gets put together. 40. We have q of x is equal to x minus 5 over 3x minus 1. Let's break into pieces. So I'm going to do domain, vertical asymptote, horizontal asymptote, intercepts, I'm also going to check for any holes, and then I'm going to need to do the fun, which is the actual graphing of it. Okay, let's do it one piece at a time. I'm going to go quick through this because we've already done a couple of examples using it. The domain. That's when the denominator, 3x minus 1, equals 0, which occurs when x equals 1/3. So this is my vertical asymptote, x equals 1/3. Okay. So that means my domain would be from negative infinity to 1/3, and from 1/3 to infinity. So if I'm going to graph this, I can go ahead and get started on the graph part of it. Hopefully this isn't a mistake, but I'm going to count by 1/3. So this first one is going to be at 1/3, 2/3, 1, 1 and 1/3, 1 and 2/3, 2, and then same thing going up and down, 1, 2. The reason I'm going to do that is because this asymptote is at 1/3. It's a vertical asymptote. This is my vertical asymptote. Okay, my horizontal asymptote. My horizontal asymptote, I noticed that in my problem I have x over 3x, which means my degree is the same, which means my horizontal asymptote is at y equals coefficient divided by coefficient, which is 1 over 3, which means my horizontal asymptote is at y equals 1/3. This can happen, but these are two different things. This is when x equals 1/3, this is when y equals 1/3. And these occur in different places. So the y equals 1/3 is actually right here. This is my horizontal asymptote. So my vertical asymptote occurred when x equals 1/3. My horizontal asymptote occurred when y equals 1/3. Okay, let's do intercepts. Come back over. Let's start with x-intercept. X-intercept occurs when the top equals 0. So that's when x minus 5 equals 0. Well, that's just x equals 5. So x equals 5 is going to be way over here. So 1, 3, 4. Oh, it's way over here. I'm just going to call it right there and hope that's 5. And then my y-intercept is when I plug in 0 for everything. Turns out my y-intercept is also at 5. So I get 0 minus 5 over 0 times 3 minus 1, which would be negative 5 over negative 1, which is at 5. But it's when y equals 5. Okay, I may have to do another one of these. That sucks. Okay, I may do it down here. Okay. All right, holes occur if your vertical and horizontal ever end up matching. So these didn't happen. What I mean is, if there's ever a hole in your domain and you get that same value in your intercept. So like here, my domain was 1/3, but notice how my intercepts were 5 and 5. So they didn't match. So there's no holes. Okay. Let me make a bigger graph. Okay, I'm going to still count by 1/3. So this is 1, 2, 3, 4, and 5. Make this 1, 2, 3, 4, and 5. So at 1/3. This is my vertical asymptote at x equals 1/3. At 1/3 on the y. This is my horizontal asymptote. And this is when y equals 1/3. My intercepts occur at positive 5 on the x and at positive 5 on the y. Nice big dots. Okay, so how do we make this look right? Well, the fun begins when you have to ask that question. Okay, so the last piece to graph these things is to deal with multiplicity. How many times did you get an answer? So for this example, in the horizontal asymptote, we got one answer of 1/3. This is an odd number. If we go way back, how many solutions there are determines how the function is going to act. So notice how there is one solution of 0. And notice how they go in different directions. One goes up, one side goes down. On this example, there are two solutions of 0. And notice how they both go up. Well, the last little piece of your notes that's really helpful is to know about the types of solutions you can have. So when it comes to graphing this thing, your last little bits of notes. So when it comes to graphing, I recommend to do the following. I want you to find the horizontal asymptotes, vertical asymptotes, and intercepts in any order, okay? And make sure you find both the x-intercept and the y-intercept. Make sure you find the vertical asymptotes, make sure you find the horizontal asymptotes. Make sure you find any holes. Okay? And then we talk about behavior. Okay. If, when you look at your vertical asymptotes, if they are odd powered, meaning they appear 1 time or 3 times or 5 times, then what that means is they're going to have opposite behaviors. If your vertical asymptotes are even powered, meaning one answer appears 2 times or 4 times or 6 times, they're going to have same behavior. Again, look at our old notes, make sure that makes sense. Look here, I have one answer, 0. How many times did it appear? Once. Notice my behavior. One side of 0 goes up, one side of 0 goes down. Here I have 0, but it appears twice. Notice both sides go up. If an answer appears twice, it's going to have same behavior. If it appears once, it's going to have opposite behavior. So, let's analyze. Behavior. I have one asymptote. My asymptote was at x equals 1/3. Notice I'm only doing the vertical asymptotes because they're the only ones that do this. So, my x equals 1/3 is my asymptote. How many times did it appear? Well, most of the time the answer is going to be 1. There are special cases when it isn't, and that's the next example I'm going to show you. But since it's 1, that means it's going to have opposite behavior. Meaning one side needs to go down and the other side needs to go up over time. So we know our options are, we could have in here doing this curve, we could have up here doing this curve, bounded between the purple and the blue every time. So inside of this purple and blue, inside of this purple and blue, inside of this purple and blue, inside of this purple and blue. We know it's going to have this curved L shape. But the question is, which one does it fit into? Well, it needs to have opposite behavior, and it needs to go through these 2 points. Well, the only way that's possible is if on this graph I have this picture and that picture. It's the only way that will meet the intercept criteria and the opposite behavior criteria. And it turns out, if we graph this thing, that's exactly what happens. Here's my graph. Pull open the one we asked about, which was x minus 5 divided by 3x minus 1. Notice y-intercept of 5, x-intercept of 5, and notice that if I graph my lines, x equals 1/3. That's right in between them. If I graph the line y equals 1/3, it's also right in between them. This middle piece will rarely be perfect, but you don't need it to be. Just make sure it has a nice curved shape. It should not come all the way in. Give it some space. Use this to guide you, okay? All right. I'm going to do at least one more, hopefully two more. Let's look at 42 now. This was 40. Look at all these pieces. Long day today. Hour and a half lesson. Ooh. Let's now go to 42. The only difference between any of the problems that I've shown you and anything that might be any harder is going to be the fact that you may have to do some factoring. And so I'll try to do 44 as well. I'll try to do this fairly quickly, and you'll see that there's no big difference. So 42. On 42 we have r of x is equal to 5 over x plus 1 squared. Let's hit it. So I need to do vertical asymptotes, horizontal asymptotes, intercepts, holes, and then behavior. Behavior should be saved for last. So I like it in this order. This is my preferred order for when I graph these. Sometimes I move holes up, but otherwise that's pretty much it. Let's do one piece at a time. And domain can be included kind of anywhere in here. So my domain, I set the bottom equal to 0. So I take x plus 1 squared equal to 0. Obviously, it's going to give me the answer of x equals -1, which means that's my first asymptote and is a horizontal asymptote. So if I'm going to my graph, it helps to wait to draw this till the end, but I'm a rebel. So my horizontal asymptote, I'm going to consistently put in blue here. This is my vertical asymptote, and it's when x equals -1. All right, my horizontal asymptote. Well, I notice that my top is less than bottom in terms of degree, right? I have no x's. I have x squared on the bottom, which tells me that it's y equals 0. Which means that my y equals 0 is going to be my next asymptote. So make sure it stands out here in purple. Boom. There is my horizontal asymptote at y equals 0. All right, intercepts. So let's do it. My x-intercepts, that's when I take my top and equal to 0. So I do 5 equals 0. You notice this is never true. So that means I have no x-intercepts. And that makes sense because I have a horizontal asymptote of 0. So it's on the axis. So I probably won't have any. But what about my y-intercept? That's where I put x equals 0 for everything. It turns out my y-intercept is 5. 1, 2, 3, 4, 5. Nice big dot right there. Okay. Are there any holes? You notice that my x-intercept, there's no x-intercepts, which means I can't compare them to my vertical asymptotes. And since neither one of these match up, that means that there's no asymptotes, there's no holes, so there's no holes. Behavior. Okay, I notice that on the bottom I have x plus 1 squared, which means I have -1 multiplicity 2. So I have -1 as an answer, but it appears twice. Because it appears twice, that means it will have same behavior. And from here, I have to use some logic. Now, if it means it's going to have same behavior, meaning they're either both going to go down or they're both going to go up. Well, you notice that there's only one of them that does that. The only way I can hit this dot is if I go up here. And since this one goes up, that means my other side has to go up in order to mimic the same behavior. Notice how we use the intercept, the asymptotes, to recognize this fact. Like, it's just as logical to put it down here, but if I put it down here, I have to make sure it goes same on the other side, and then it doesn't pass through my black dot. So I know these bottom two are not right. And I know they have to go in the same direction because it has multiplicity too. And if I graph this one, I have an x-intercept. Oh, sorry, I have an x equals -1. I got my asymptote. I got my y equals 0, my other asymptote. There it is. Pretty cool, right? It's the ability to take a function and write out its pieces. Now, there are questions in your homework that ask you to go backwards, to ask you to write your equation. There's some great examples of this in your text right before this. They're right here. I would strongly suggest you take a look at that. Please look at example 12, okay? I can't stress this enough. The last thing I would tell you is look at example 12. I cannot stress enough. For those last couple of problems, look at example 12 to help you out. It is very helpful if you look at it, okay? Wow, hour and 26 minutes. That is a long day. I hope I didn't kill you. If I did, I'm sorry. Better luck next time. Hope you respawn soon. Don't forget your homework assignment. It's shorter than many of your other ones because each of these problems just takes a lot of time and a lot of effort. So make sure you're keeping track of all your parts. Note each of the pieces we found today and how we found them, as well as your new notation for arrow notation. Today was section 5.6, Rational Expressions and Functions, page 431/449, 7 through 63, every other odd, and that'll be it. Remember, post any questions you guys have. I'll make any videos I need to on Saturday, and I'll see you guys next time.